Hello everybody, welcome to this next video on numerical analysis. So in this video we are going to start a new chapter named Interpolation, and in this chapter we'll start with Lagrange interpolation. First of all, I'll explain the meaning of interpolation. So what is interpolation? What do we mean by interpolation? Suppose you have a data. Suppose you have a data like this. You have x naught, f of x naught, x1 f of x1, x2 f of x2, and x3 f of x3. So you know these 4 points. So it means that you have something like this. Here is your point x1, x0, x1, x2, x3, and then you correspondingly you have some values like this. Now, an underlying function, f function, I don't know. I just know these 4 values, and somewhere in between these these data points, for example here, between the interval x0 to x3, so whatever is your initial data point and the last data point, in this interval somewhere you want to approximate the value of f. For suppose this is the point P, you want to approximate f of P. Okay, so where practically you use these things. For example, you do some experiment. If you are doing some experiment, suppose you are measuring the temperature of a furnace, and you are taking t is equal to 1 second, maybe temperature you have noted something t naught, then at 2 second 3 4 5, t1, t2, t3, t4, and after that you just close your experiment, and maybe after 5 days you are doing some analysis and you came to know that you need the value of the temperature at 2.5 also, but you don't have that value. So you have two options: either you repeat your experiment, which will be costly and time consuming, or you seek the help of mathematics. So what mathematics will do, so basically this process I told you that somewhere in between you can compute the value of the p of f of p. So this process is called interpolation. Why interpolation? Interpolation means inter means somewhere in between your data points. So p cannot be here. If you take p here, you cannot interpolate at this point. The point should be inside somewhere. Okay, so you can seek the help of mathematics. So basically you can use interpolation. So now let us see how we can do interpolation. So you have, again I'll draw a picture. You have this situation x0, x1, x2, x3, and you have some points, some values at these points, and everywhere in between I want to know the value. So one of the ways, you just fit a curve in passing through these 4 points. Fit a curve passing through the 4 points given, 4 given points, and now whatever is your p, just go to your curve, and this value is your approximation for f of p. Now the question is, what curve we should fit, what type of curve we should fit. So in this case, the simplest curves which can be used are the polynomials. There can be other types of interpolation also, and we will discuss also other types of interpolation, but for now, to start with, we will fit a polynomial curve. So we will fit a polynomial passing through our data points. Now, there are many techniques to fit this polynomial. One of the technique is Lagrange interpolation. Lagrange is the name of the mathematician. He has given an algorithm to fit a polynomial passing through your data points. So this is what we are going to discuss, and there are other techniques also to fit the polynomial that we will discuss later. So now we will start with Lagrange interpolation. What is Lagrange interpolation? Suppose I give you two data points, x0, y0, x1, y1. You have this x0, y0 point, and this is a point x1, y1, and this is my situation. This is my x-axis and this is my y-axis, and this is x0, this is your x1, and I want to find out the value of the function, approximate the value of the function everywhere in between x0 and x1. So how I can do that? I know passing through 2 points there is a unique straight line. So I know passing through, we know that passing through 2 points there is a unique straight line, unique linear polynomial. There cannot be any other polynomial which pass through these 2 points, and we know how to find out this polynomial. For that we know how to write the equation of the line. So you can simply write y minus y1 upon x minus x1 is equal to y1 minus y0 upon x1 minus x0. So this is the line of equation of the line passing through 2 points. I'm just rewriting this equation. So I have y is equal to, you can see I can write it like this, y is equal to, I'll write it first and then you can verify, x minus x1 upon x minus x0 into y0 plus x minus x0 upon x1. Here you have x0 minus x1, sorry, x1 minus x0 y1. So you can see that you can just take this on the other side. You have y is equal to y1 plus x minus x1 upon x1 minus x0 into y0. I'm sorry, here you have this also, this factor also, y1 minus y0. Okay, y1 minus y0 into x minus x1 upon x1 minus x0. Now you can separate y1 term. So you have 1 plus x minus x1 upon x1 minus x0 into y1 minus, or you take it plus y0 into x minus x1 upon x0 minus x1. So this is the first term, I have written it here, and now you just add these two terms and you will get this. So this is the polynomial which passes through the 2 points x0 and x0 y0 and x1 y1, and this is the unique one. There cannot be any other polynomial passing through these 2 points, polynomial of degree 1. Okay, so this is one thing. Now let us go for polynomial of degree 2. Now suppose you are given 3 data points. So you have this situation, x0, y0, and then you have x1, y1, and then you have x2, y2, and passing through 3 points there is a unique polynomial of degree 2. There cannot be any other polynomial of degree 2 passing through these 3 data points, and at most 2. Sometimes if your points are collinear, then the degree of the polynomial is going to be 1 only. So passing through 3 data points there is a unique polynomial of degree 2. Now how can we find that polynomial? So you can go like this. You assume that your polynomial is of this form. Now you want this polynomial to pass through these points x0, y1, y0, x1, y1 and x2, y2. It means that you want y0 is equal to a0 plus a1 x0 plus a2 x0 square, and y1 is equal to a0 plus a1 x1 plus a2 x1 square, y2 is equal to a0 plus a1 x2 plus a2 x2 square. Now these are the numbers, these are simply the numbers. So you have an equation, 3 equations and 3 variables. Your unknowns are a0, a1 and a2. So you have 3 unknowns and 3 equations. You can easily find out, a0, a1 and a2, and finally your polynomial is of this form. I am writing the form y of x is equal to x minus x1 x minus x2 upon x naught minus x1 x naught minus x2 into y naught plus x minus x naught x minus x2 upon x1 minus x naught into x1 minus x2 into y1 plus x minus x naught x minus x1 upon x2 minus x naught x2 minus x1 into y2. So this is the form of the polynomial. So did you observe a pattern? This is the second degree polynomial passing through 3 data points. And the first degree was when you had 2 data points x0 y1 naught and x1 y1. The polynomial was, which we have written above, is x minus x1 upon x0 minus x1 into y0 plus x minus x0 upon x1 minus x0 into y1. So this was the polynomial. So on the same pattern, suppose you have given 4 data points. So you have now, if you are given 4 data points, say x0 y0, x1 y1, x2 y2, x3 y3, there will be a unique cubic polynomial. There will be a unique cubic polynomial passing through these data points. Passing through these data points. And that polynomial can be written as, first you see here, you in the numerator you don't have x0, here in the denominator you don't have x1, and here you don't have x2, and in the numerator you are replacing x with x0, here you are replacing x with x1, here you are replacing x with x2. So what you do, you write it like this, and you can actually verify it also. You'll get this. In the numerator first you don't use x0, so you have x minus x1 and use all other data points. So x minus x2, x minus x3, and in the denominator replace x with x0. So you have x0 minus x1, x0 minus x2, x0 minus x3, and multiply it with y0, and plus you add, now you don't use x1, so you have x minus x0, x minus x2, x minus x3, and in the denominator replace x with x1, so you have x1 minus x0, x1 minus x2, x1 minus x3 into y1, plus now you don't use x2, so you have x minus x0, x minus x1, x minus x3 upon x2 minus x0, x2 minus x1, and x2 minus x3 into y2, plus you don't use x3, so you have x minus x0, x minus x1, x minus x2 upon x3 minus x0, x3 minus x1, x3 minus x2 into y3. So this is how you write the polynomial, right? And so on. Now if I have 5 data points, then also I can write. So in general, if you have n data points, n plus 1 data points, in general, if you have n plus 1 data points, if you have n plus 1 data points, say x0 y0, x1 y1, x2 y2, and xn yn. So these are n plus 1 data points because I am starting from 0. So these are n plus 1 data points. Passing through these n plus 1 data points, it is a unique polynomial of degree n. Passing through these n plus 1 data points, there is a unique polynomial of degree n of degree n. Now how can I write that polynomial? I claim, which can be written as y of x is equal to L0 x y0 plus L1 x y1 plus L2 x y2 and so on Ln x yn, where in L0 we don't use x0 in the numerator, so you have x minus x1, x minus x2, x minus xn upon, you replace the denominator in denominator x with x0, and in li you don't have x minus xi in the numerator, so you have x minus xi minus 1, x minus xi plus 1, x minus xn divided by, in the denominator you replace x with xi, so you have x minus xi minus x0, xi minus xi minus 1, xi minus xi plus 1, and so on xi minus xn. So in the compact form we know that product can be written as pi, so this is pi x minus xi, I not equal to x minus xj, j not equal to I divided by pi xi minus xj. Okay, so this is j not equal to I. So this is how you write the polynomial in the compact form. So you can write your polynomial as y of x is equal to L naught x y naught plus L1 x y1 plus Ln x yn, where Lix is equal to product j from 1 to n j not equal to I x minus xj divided by x minus, and you can simply write it here, xi minus xj. You don't have to write it separately. So this is your Lix. So this is the required polynomial. So this is called Lagrange interpolation. Now let us do one problem. So you have determined the linear, question is determine the linear Lagrange interpolating polynomial. Determine the linear Lagrange interpolating polynomial passing through 2, 4 and 5, 1. So what you can do, it's very simple. Simply you have to know the formula. You have yx is equal to x minus, first use this data point 5 upon 2 minus 5 into value, that is 4, plus now use x minus 2 upon 5 minus 2 into value 1. So this is equal to minus x plus 6. So this is the required interpolating polynomial. Now suppose you have given 3 data points. So let us do one more problem. Question is, so you have these data points 2, 1 by 2, 2.75, 1 by 2.75, and then you have 4, 1 by 4. Question is, find the quadratic polynomial passing through the above 3 data points. The quadratic polynomial passing through the above data points, polynomial passing through above 3 data points, 3 data points, and use this polynomial to approximate at x is equal to 3. Can you find the error? Okay, so let us do this problem. First of all, simply you are given 3 data points and you want to find out a quadratic polynomial. So for that you do like this. First you use, your polynomial is going to be, first you don't have to use this data point, so you have x minus 2.75, x minus 4 divided by, in the denominator you replace x with 2, 2 minus 2.75, 2 minus 4 into value of the function, that is half, plus, now you don't use the second data point, so you have x minus 2, x minus 4 upon 2.75 minus 2, 2.75 minus 4 into the value of the function, that is 1 upon 2.75. Now you don't use the third data point, so you have x minus 2, x minus 2.75 upon 4 minus 2, 4 minus 2.75 into value of the function, that is 1 by 4. So you just find out this polynomial. This polynomial is equal to 1 by 22x square minus 35 by 88x plus 49 by 44. Now the next part of the question says, use this polynomial to approximate the value at x is equal to 3. So you have y of 3 is equal to 1 by 22, 3 square minus 35 by 88 into 3 plus 49 by 44, and this is equal to 0.32955. Now the question is, can you find the error? Now for finding the error, you should know the exact value. Now look at your data. Data is basically 2 is equal to 1 by 2. 2 mapping to 1 by 2. 2.75 is mapped to 1 by 2.75. 4 is mapped to 1 by 4. It means that f of x is equal to 1 by x. So looking at data, we can observe that The underlying function is 1 by x. So exact value of f of 3 is 1 by 3, that is 0.3333. So error is proximate exact value, that is 0.3333 minus proximate value 0.32955. So this is your answer. So this is how we do the Lagrange interpolation.